Okay. Hello, everyone. Let's start with the with everyone. Can you guys hear me? Everything is clear. Sounds good. Okay. So this is gonna be my last presentation. It's gonna be hopefully less than an hour, and I want to give you a brief description of what we are doing with the traveling wave tube amplifier. This morning, you have had some background about traveling wave tube in lower power regime. Now, if we have higher power, things will have slightly changed. So you need to consider some aspects. So, okay, cool. So let's pick up from where we left yesterday, which is basically dispersion relation, dispersion characteristic. You guys now, I think, hear dispersion relation, dispersion curve, dispersion characteristic many times. Is basically omega versus phase shift or wave number. And this is very important when you are including some periodic structure or studying some periodic structure as we described it yesterday. So just to refresh your memory, that we usually plot on y-axis the real part of the frequency. Now I'm adding more extra information, real part, and this is the phase shift or the wave number multiplied by the period of this periodic structure. Now, what you see in the dotted line is the smooth wall waveguide. We call it smooth wall waveguide. The regular waveguide you have studied probably, and this is just a pipe, could be cylindrical, could be rectangular, could be elliptical in some cases. So this is very nice, showing you like how they construct the dispersion curve from smooth wall waveguide, and this is what you see here. Basically, you're gonna end up with a stop band, and some higher order modes are a mix of two or more of the smooth wall waveguide modes, TM01, TM02, TM03, if we are describing linear devices, TE mode for circular devices, because this the field component or favorite field component that we want. All of these, we call them cold dispersion relation. And this is exactly the same as this. I'm just having different examples. Now, it depends on the where your electron beam dispersion line you're gonna enhance or introduce instability for certain source. You're gonna either have forward wave, backward wave, and either you're gonna have an oscillator or an amplifier, and this is what we wanna do. So this plot is showing you that if you are here, you are probably doing backward wave because the slope at this point is negative. And if you have the operating point, the electron beam right here, you are positive slope, that's forward wave. And this is what you see here, forward wave, backward wave. And each one of these, at any operating point, you can design an oscillator or an amplifier, could work. But from people experience, they have tested this before, and they found that for linear devices, if you wanna operate as an amplifier, you wanna pick the forward wave because this is more efficient. And more efficient means like the instability that you introduce to the electron beam, and this is all plasma science part. The instability is convective instability, and this is convective instability. Basically, the wave grows as the electron beam instability introduced. So this is kind of a like next step once you start, understanding about high power microwave sources, and you want to design them. You want to study plasma science as well. Now, once you introduce the electron beam, your slow the dispersion curve is not going to be smooth anymore. Things will change. Okay, and this is what happened actually when they are coupled, the electron and the electromagnetic wave coupled. It depends on the current, the instability that you introduce either is going to have a kind of a good range that you can control, and this is for low current regime. But for high current regime, the instability is really small. And instability, this is how the generation happened, because you have electron beam coming to your interaction region, is kind of a DC uniform. It doesn't give you anything. You need to introduce perturbation, modulation, punching, and then deceleration to extract the power. And all of these processes basically instability to the electrons. Electrons want to just go in a line, like every single one is just having some charge. And this curve here is real omega, real frequency, right? And now each one of these parameters, frequency and wave number, they are actually complex numbers. Okay, so they have a real part and imaginary part. And the imaginary part for the frequency is basically the temporal component, right? Remember yesterday we wrote the exponential function ej omega t, we call it temporal component, and ej beta z, which is a spatial component. And the wave number, is going to be responsible for the spatial behavior. Now, the growth rate is basically related to the imaginary part of omega. And you notice that this is the growth rate, and this is the region, what you see here, the small region here. So if you miss this region, if your energy like you are losing energy, or like you have too much energy, you actually are not interacting. You are not generating RF. So it's really very small window that you can work with. And that's very challenging, in fact. Now, you can, study this in more depth, that if the interaction, has this behavior, is going to be in, I'm just describing here as V1 maybe is the beam. Yeah, V1 is the beam mode, slow space charge wave, and V2 is the slow wave structure eigen mode, electromagnetic. And if the instability has this behavior, or the intersection has this behavior, is not going to introduce any instability, and means that there is no generation. And if the intersection between them has this behavior, will have unstable intersection, and then you can introduce some type of instability. And this one called convective instability for traveling wave tube, for backward wave oscillator BWOS called absolute instability, as the wave grows everywhere. That's that's kind of like advanced topic for microwave engineering or microwave tubes. Okay, so today we are trying to have some information about amplifiers, and in the morning you had like some good background about traveling wave tube and at a lower voltage, lower current, lower power regime. But I think I have described this before, but in any case, oscillators start generating RF from noise, okay, because of the geometry, because of all the choices that you made when you are designing the source. You're gonna have a resonance at some frequency and grow your signal. For amplifier, you have to introduce seed signal or input signal to your structure, and hopefully this will be amplified, and then you extract it somehow. Oscillators, you can't start oscillating unless you pass certain current called starting current. This is a threshold that if you don't pass this current, you don't have as high current as threshold current or higher, you are not generating RF. For amplifier, you need to operate less than the starting current of oscillation. So now for an amplifier, you have two things that you need to think about when you design your amplifier, of course, bandwidth and the gain. For oscillators, we are thinking about how to get power and how to exceed the starting current, of course. Okay, so what else here? I have many points here. If you are interested, I think I'm gonna post this, or I'm gonna upload this. But this is kind of comparison between the amplifiers in general and oscillators. And this is not only for linear devices. This is for any slow wave structure based, or maybe even for any oscillator and amplifier. The oscillator will start oscillating when you provide what we call feedback, right? If you have to have a feedback. And for these devices, the feedback comes from the reflection from the edges. So at the edges, you're going to have some reflection happen. And this is what's going to cause the feedback and grow the signal. For amplifier, you don't want to have a feedback. You have to reduce the reflections at the end of the structure. That's why now a lot of techniques that they pay attention how to reduce the reflection from edge of the, or where's the extracting, especially where you're extracting the RF. So this is very important. And now let me move on. So Helix traveling wave tube, this is first traveling wave tube for lower power, is very great amplifier with a wide bandwidth. But you can't push it for high power because this small helix will be, will be having a lot of RF voltage around them, RF fields, and they can cause RF breakdown, and you could damage them. So people have an idea of having coupled cavity traveling wave tube. It reduces the bandwidth. Whenever you hear cavity, means like there is a high Q. Whenever you have a high Q structure, you mean have small bandwidth. But you can generate high power, really high power, megawatts or gigawatts, probably gain from 20 to maybe 40 dB. And now, when we are talking about megawatts at the output, that means you can't have an input signal, small input signal like watts. You have to have your input signal kilowatt level in order to get the megawatt level, because the gain usually 20 to maybe 40 dB for this type of structures. There is a variety of different types of coupled cavity or slow wave structure type of different geometry, as you can see here. People come up with the variations from Helix for different purposes. But what I want to just focus on the slow wave structure type of traveling wave tube, as you see here. Those are two main amplifiers that they achieved very high gain at X-band, one in United States and one in Russia in early 90s. Schiffler work here, and here this is the group from Institute, I think, of Applied Physics. Anyways, so if you compare this with what you saw yesterday, do you remember the slow wave structure that we used for backward wave oscillator? Well, it was kind of a sinusoidal corrugations or rectangular corrugations, but you did not see this small transition, right? And this is the main purpose of using this, is to reduce the reflection at the edges. So to minimize the feedback as low as possible. You don't want to have feedback, otherwise your amplifier will break to an oscillator, and you don't want that. You want to have an amplifier. You want to amplify your seed signal to the output. That's why this is very careful. We designed this carefully. Again, once you inject your signal, there is no reason that the signal will follow the path you are hoping to go toward the output and amplify. Some of the power will go here toward the cathode unless you do something about it. You're going to add some reflection here, right? But this reflection is not going to be interacting, like it's not going to be in the interaction region. It's not going to contribute to oscillation, just like for input signal, seed signal. So that's some people, like if they don't know about, this field, they start to having the reflection maybe here, or maybe like they have a slower structure, like continue to whole of this region. That's going to be bad for your amplifier, because if you introduce reflection at the edge, that means you are enhancing the feedback. So you don't want to do that. So we have a project currently. I'm going to show some results here. And probably I'm going to delete some of these results when I post this, because it's not unpublished still. But the project that we have right now is the idea is coming, I think I mentioned this, idea comes from low helix traveling wave tube. When you have multiple beams that chosen with the different velocities, you could increase the bandwidth and increase the gain, have a wider bandwidth and increase the gain of the amplifier. That was done at lower power, lower voltages, and for lower voltage helix, you can actually control how to drive these cathodes. Basically, you can have two power supplies and drive them. For high power microwave, this is not, it's not possible, because the structure is really, connected to an accelerator is not possible. So the study that we are doing is called two-stream traveling wave tube. And in order to have two-stream traveling wave tube, you want to design regular traveling wave tube, high power traveling wave tube with single beam first, then you can introduce the second beam. All of these results that people have done, they just have a rough approximations with the equations and then design, and then they test it. They don't have much of computer simulation back then when they did the experiment. So revisiting these was very challenging task. We could not replicate the results. And we have two PhD students working independently, in the same project, but different universities, UNM and the University of California, Irvine. And basically, this is the idea. It's basically two velocity beams. And people have done it with the low voltage, if you can control the different cathodes with different electrons. This is relatively easier, because controlling this by having two power supply is possible. And these are the publications that people have done in the 40s. Now, I showed you yesterday two electron beam, graphite type of two electron beam. And that is basically what you see here. And people have worked with the regular gun with two electron beam, with two energies or two velocities. I think the difference is 20%. And also some studies have been done for klystron, for two beam klystron, and the results were promising. So first step, always when we do high power microwave, we are trying to design high power microwave device, we start with the cold test. We just ignore our beam for a second and start optimizing our structure with no electron beam. This is the first step. I showed this yesterday. Do you guys remember what we are doing here for our structure? Is basically ping your structure. You send impulse and try to see what frequency will grow. So pinging the structure is the first step. And then you're gonna try to find these resonances. And at each of these resonances, you're gonna study the mode. Is it your mode of operation or not? If you find the mode at this specific frequency is TE mode, you just ignore it. It's not going to be part of your dispersion curve. It's not going to be part of your design, because there is no axial field component and your electron going in the axial direction. So it's meaningless. So these are some points, and we are like just closely monitoring the mode. This what we call cold analysis, cold test. And I'm using here Magic, which is software that is legacy software, is not, you can't buy it anymore, but we still have it and we still use it. It's very good software. Magic pick code is based on Fortran, and it has, of course, an eigenmode solver and pick code solver. So first we studied how to get these correlations, what shape is the best shape, and also we compare with the previous results, because previous results, they don't show exactly what's the shape of the structure. If we go back, let me go back a couple of slides. If you take a look at this one, you can't be certain, is it sinusoidal corrugation or maybe, rectangular with the rounded edges, so could be all of these variations, and you will maybe ask, what's the difference, right? And now we want to see what's the difference. The difference is going to come from okay, got stuck. Okay, good. To the right slide. This is the difference. See, this is rectangular slow wave structure and rounded and then sinusoidal. The dispersion curve, this is frequency versus phase shift, which is related to the wave number. As you change, like a small change, this is not like huge different shape. Everything is fixed, the period is fixed, the depth of corrugation is fixed, but we are just changing this slightly, and we are getting slight different dispersion curve. That's why dispersion relation is the starting point for our studies. That's good. And if we review this with the previous results, as we compared the dispersion curves, we found that the dispersion curve is something like close in between here. It's not exactly like the sinusoidal or rounded. And I'm talking about the tested one in experiment. Do you guys remember how to get the dispersion curve from experiment from yesterday? VNA, right? You have a VNA and launch the mode launcher, and you NCAP vector network analyzer in the lab. But your vector network analyzer should cover the frequency range. Here is expand from 8 to 12 gigahertz. Again, CST is very powerful if you just have an ideal case where you have one period and then you tell CST that, okay, this is a periodic boundary condition, means repeat this to infinity from both sides. And it's going to give you smooth line, what you see here.
This is 1 unit cell.
1 unit cell, but periodic boundary condition.
Yes.
So basically, CST will consider going to infinity. Yes. Yeah, so you have to choose the boundary conditions.
Yes.
But for Magic and most kind of related to the experiment, you're just gonna have to come up with number of periods that you want to study. I think here's the maximum number of periods is 11 here. So you're gonna have one period, two, maybe 2 and 4, 6 to 11. So you change it and you see how things behave. Okay, so this is the dispersion curve for sinusoidal corrugation, and the previous one is for rectangular corrugations, and they are very close to what we got from HFSS. There is like advantage and disadvantage from using multiple software tools, and the reason why, because the mesh for different software is different. So for maybe Magic, if you see the staircases here, is really, you can't go like very fine mesh in this case because it's going to be memory consuming. So you need to compromise this, and having a second software to check the dispersion curve is a very good idea, actually.
May I ask a question?
Yeah.
Did you use adaptive mesh CST?
No, I don't think we used the adaptive mesh. We made sure.
Mesh refinement time.
Yeah, is calculating and then they refine.
And then refinement.
Yeah. Yeah, I think if you want to like very accurate results, once run like so
So
basically
the solution or convergence criteria may be emerge.
yes.
Mhm.
But this is gonna take longer time to run
Yes.
the simulation. So usually what we do, like we design and we get an idea, and then we have one run that have a very fine mesh or refined mesh and line, and then like wait for it for days maybe, or
Takes very long time.
yeah. Oh, especially for pick code, once you introduce particle, you sometimes wait for 2 weeks for your simulations are calculated. And if you have power outage, you start from zero. Everything is gone. So second thing that you need to optimize is the input coupler. Input coupler, how to inject your RF. Is it going to be one arm or two arms or maybe multiple? And you have to optimize this without the electron beam. And then once you introduce the electrons, you have the beam loading, it changes a lot of your design. You might need to have a knob to adjust. So these are some other ideas how to do the input coupler from the Fuchs and others. So this is very based on path of rays. So the input coupler is basically coupling from a rectangular waveguide TE10 to circular waveguide TM01. It's magnetic coupling, because if you take a look at the magnetic field, you'll see it's not electric coupling, it's magnetic coupling. But the thing is, for high power, you don't want to have two ports. It's very hard to have kind of a splitter in high power. If you have like 100 kilowatt input signal and you want to split it, you're going to end up with a very challenging structure. So you want to have one side, you inject your RF power, and the second one, you might use a plunger to tune it. So basically to adjust and have, the optimum coupling. So this is a study for two arms input coupler, means like we are injecting the same RF, probably 250 here, I think, and see what's the output power. Here we're just like injecting input power and measuring at the output. We see the reflection coefficient and transmission coefficient, basically S11 and S21 in real life language. And you have to have a certain frequency that you picked for oscillation. This is the input power or input mode for the rectangular waveguide. This is the output mode for circular waveguide here. Input coupler from one arm, I think this one. So the study for the single arm or double arm is really tuning, basically. You run like a lot of simulation to find the optimum, the sweet spot that you want to work at. So these are just different tuning points. I think I can run this this one when we found the optimum point. This is basically the coupling. Is not running all the way, but you can see the mode, how the mode is coupling from rectangular to. Okay. Now that one, the one I previously showed you, just shows you this part right here, the rectangular and circular section. But now if we introduce the slow wave structure, the impedance will change, and you need to make sure that your input coupling is still okay, and you're still coupling the same amount of power. And the reason why, because you don't want to have a lot of reflection. If you don't couple all the power, you have reflection back to your source here, the seed signal. And for 100 kilowatts or 250 kilowatts, you don't have a circulator that, I mean, like, is really, is really expensive even for a couple of kilowatts. And if you go to hundreds of kilowatts, that's really expensive part that you don't want to invest in. So you want to have minimum reflection that is not affecting your source. Now this is the study for the whole structure, and we are injecting the beam, and we study like the input coupling, how it's changed, and what's gonna happen at the output. You see here, there is mode competition. Whenever you see this, there is mode competition, and the problem is that your amplifier is working as an oscillator as well. We have both, and that took a year from students, like optimizing things, changing. Yeah.
The middle of this here.
This one, energy plot.
Energy.
Yeah, this is energy versus distance. Is it axial distance? This distance.
Can you comment this plot?
This one? Yeah. So basically, the energy comes from the electron and to the interaction region and start modulating. You are modulating your electrons, right? And then at the end, you see here, most of the electrons will be decelerated, means like they are losing energy. Yeah. So I have a small video that shows you the process over time.
Electron velocity figure?
Similar to this, gonna be. Yeah, very similar to this. This is the energy.
So we can say at the end of the distance, then we say
here
it goes to saturation.
So basically, the electrons will be trapped and
trapped. Yeah,
it's gonna be trapped. Yeah, so Landau damping, I think they call it.
Velocity trap.
Yeah, this is plasma science thing, So you can optimize this. That's why you have a limited length.
Yes.
So ideally for amplifier, as you increase the length, you increase the gain. But you can't do that. You can't have any length.
You do saturation.
Yeah, you reach this like the trap of the electrons, and you start
nonlinear region.
Yeah, and electrons start taking the RF power out of your system. Okay, so maybe like I walk you through these figures, all from magic. That I'm not, I did not do a good job showing all the numbers, but basically here is the RF voltage at the output. Sorry, this is RF signal here, and this is the RF signal at the output here. So this is the input frequency for this, and this is the output frequency. What we are injecting, can see 9 point something, right? And we're getting the power. This is 9.3. We are getting another peak, and this is basically oscillator. So we are not amplifying the input signal. We are generating another frequency. So this is wrong. This is not the way we want our amplifier to work. So we thought that our starting current, our beam current, is higher than starting current. So we start reducing it so that we prevent the oscillation. And this is basically what you see here: 1 kiloamps beam current. And then we allow only a portion of that to go to the interaction region, because if we go back here, we are using this piece right here to shave our beam, to get rid of some of these electrons and allow only small electrons to go here, small current. So this is 350, 175. And here we are changing, in this direction, we are changing the magnetic field. We thought that if we work at the cyclotron magnetic field, we can prevent oscillation for TM01. Now we introduce second beam just for fun, and this is, look, both of them, they are having this modulation behavior. These are two beams, two electron beams. Let me jump. Now we optimized our structure in a way. We changed it, you know, the parameter that we can change for the geometry, and we are, you know, here in this study we are testing how many taper periods that we need to add here in order to find the optimum non-reflection, no feedback, but in the same time we still have good amplification. I'm going a little bit fast. So this is one of the studies we have at 9 gigahertz, and the middle section 11, 12, 13 corrugations. This one, the middle section, the uniform section, and then we start changing these from 0, 1, 2, 3 all the way to, yeah, here we change the number of taper periods. And we want to see how the insertion loss behave as we increase number of these tapers. So we found that at 3 or 4 periods for the taper is the best solution for non-reflection. This is another plot, but it's still energy. Huh? Okay. Look, this is the real time. This is an electron going in spatial coordinate, and you see how the modulation happens in the top. One more time. You see the pulse time, like here, 5, 7, 8, 9 nanosecond. This is during the pulse. This whole event happened, you know. And yesterday you saw the mode is basically very fast. This is another one. I think it has all of the, the beam and the energy of particles and also the input signal as well.
It's a nice one.
Yeah. So now the problem is always for these devices is here. Here we are using a mathematical function for the magnetic field, how to taper the electrons, because we are extracting here. Remember, for low power traveling wave tube, you inject the signal from the side and you remove it from the side or extract it from the side. For high power, you can't do that because of the breakdown issue. So you have to generate or radiate from the aperture here. And you need to stop your electrons. You don't want your electrons go and hit your window and then break the vacuum. This, sometimes if you don't design it carefully, you will introduce some instabilities to your device. And sometimes if you just go too fast here, you start adding some instability and might change the feedback for your device. Yeah.
Here, you designed some sort of crab cavities or?
No, corrugations, shallow corrugations. It's not very coupled cavity in the sense of high depth. Yeah, it's very shallow corrugations. Shallow means like is fraction of the wavelength. Yeah, so there is too many. Still, this is like ongoing research, but we finally had like kind of like 10 to 20 dB gain. These data points are kind of over promising, but I think the last data that we made sure that everything is correct is 10 to 20 dB for single beam, and now we're ready to have the second electron beam to see if we can enhance the gain of that type of slow wave structure. Okay, so any questions about the high power traveling wave tube? So I think one of the slides. Any question? Is everything? Yeah.
Hello.
Yes, I can hear you. Go ahead.
Yes, sir. Sir, how two different kind of velocity electron are generated in the in your system?
Okay.
Is it different kind of power supply are giving, or the electron source structure are changing?
So for low power helix traveling wave tube, you can have two power supplies to control the voltage applied between the anode and each one of these cathodes, or two or more. But for our
Okay.
high power accelerator, you only got stuck with one voltage applied between cathode and anode.
Okay.
So
Then how?
yeah,
Yes.
I'm coming to your question. So the contribution that UNM did is they did the study. If you have nested, they call it nested cathode, where you have two kind of concentric cathode. I showed the picture here. You see it here?
Yes.
Yeah.
Yes.
And now this is the one, outer one has slightly larger radius, but you control the distance. The inner one, how much is sticking out. If you have both of them, they are same length, you are not generating any electrons from the inner cathode. But if you change it away, closer or maybe longer away from the outer one, you could change the energy and
Velocity.
yeah.
Yes. Velocity. Okay, I understood. That's the only, and it is present research here. Is it right?
Is
Okay.
there is a couple of publication about the cathode, nested cathode. We have already published this results, but for the traveling wave tube, we're still trying to use this type of structure for cathode structures for the traveling wave tube.
Okay.
Okay.
Yes. Okay. Somehow, if we anyhow, if we disturb the velocity, second one, then velocity will be different from each other. So this is the one way. Maybe okay. Thank you, sir.
Okay, thank you. Any other question? Okay, so either it's too clear or it's not clear at all. One or the other. Okay, thank you, and thank you for the
questions
question on the
from Zoom.
this message is being recorded.
Ali,
You can ask.
sormak kalkıyor.
They raised their hand.
Yes.
Okay, by accident.
Okay, there any question? Anyone else?
No question.
No question.
Yeah. Okay, so this is my last presentation. I would like to thank the organizer for this very nice workshop and for making everything as organized as possible. And I'm glad to meet all of you guys. And I hope we can continue meeting in the future and exchange knowledge, Inshallah. Okay, thank you.